The early 20th century, a crucible of scientific discovery, forged quantum mechanics, a revolutionary lens that fundamentally reshaped our view of reality. Pioneers like Max Planck, Albert Einstein, Niels Bohr, and Werner Heisenberg peered into the subatomic realm, uncovering a universe far stranger and more counterintuitive than anything classical physics had painted. At its heart lay a profound conundrum: the measurement problem. In the quantum world, particles do not snap into definite form until observed. Instead, they shimmer in a superposition of all possible states simultaneously. A quantum electron, for instance, might be a blurred swirl of spinning both clockwise and counterclockwise, or a ghost flickering in multiple locations at once. This concept, while mathematically precise and empirically accurate in predicting experimental outcomes, presented a deeply unsettling philosophical challenge. How could a particle exist as a wavering phantom? And what precisely constituted a measurement that forced it to choose a single reality? The act of observation, it seemed, played a crucial, active hand in shaping the very fabric of existence, a notion that clashed violently with the classical view of an objective, observer-independent universe. Niels Bohr, a central architect of quantum theory, along with Werner Heisenberg and others at the Copenhagen Institute, formulated what became known as the Copenhagen interpretation. This interpretation, while not without its critics, became the prevailing lens for decades. It posited that the act of measurement causes the quantum wave function, a shimmering cloud describing probabilities, to collapse into a single, definite outcome. Before measurement, the quantum system is a probability distribution. After measurement, it is a concrete reality. But the Copenhagen interpretation remained conspicuously silent on how this collapse occurred, or what precisely defined a measurement apparatus that triggered it. It was a pragmatic solution, allowing physicists to make accurate predictions, but it left a gaping hole in the conceptual framework of reality. The inherent strangeness of quantum mechanics and the ambiguity of the measurement problem deeply troubled many physicists, perhaps none more famously than Erwin Schrödinger. In 1935, Schrödinger, in a thought experiment designed to highlight the absurdity of applying quantum superposition to macroscopic objects, introduced his now iconic cat paradox. Imagine, he proposed, a cat sealed inside a steel chamber with a flask of hydrocyanic acid, a Geiger counter, and a tiny bit of radioactive material. The radioactive material is so small that, within an hour, there is precisely a 50% chance that one atom will decay and a 50% chance that it will not. If the atom decays, it triggers the Geiger counter, which in turn releases a hammer that smashes the flask, releasing the poison and killing the cat. According to the Copenhagen interpretation, until an observer opens the box, the radioactive atom exists as a blur of both decayed and undecayed states. This quantum uncertainty, Schrödinger argued, would then extend to the macroscopic cat. Before observation, the cat would be simultaneously both dead and alive, a grotesque and illogical state. This thought experiment was not meant to be taken literally, but rather to expose the profound conceptual difficulties arising from extending quantum rules to the everyday world. If a cat could be simultaneously dead and alive, what did that imply about the nature of reality itself? The paradox starkly illustrated the boundary problem. Where did the quantum world end and the classical world begin? Where did the wave function collapse? Was it at the atom, the Geiger counter, the hammer, or only when a conscious observer looked inside the box? Albert Einstein, a fierce critic of the Copenhagen interpretation, famously declared, "God does not play dice with the universe," expressing his profound discomfort with the probabilistic and seemingly indeterminate nature of quantum mechanics. He, along with others, yearned for a more deterministic and objective description of reality, one where particles possessed definite properties independent of observation. Einstein, Boris Podolsky, and Nathan Rosen further challenged the completeness of quantum mechanics in their 1935 EPR paradox, proposing that quantum theory must be incomplete because it allowed for spooky action at a distance, a phenomenon later confirmed by experimental evidence in the form of quantum entanglement. While the EPR paradox didn't directly address the measurement problem, it underscored the deeply counterintuitive nature of quantum correlations and the struggle to reconcile them with classical notions of locality and causality. For decades following the 1930s, the Copenhagen interpretation, despite its conceptual shortcomings, held sway. It provided a working framework that allowed for astonishing progress in fields like nuclear physics and solid-state electronics. Physicists learned to shut up and calculate, embracing the practical utility of the theory, even if its philosophical implications remained deeply unsettling. Textbooks presented the wave function collapse as an axiom, a given without fully explaining its mechanism. The question of what constituted an observer, or at what point in the chain of events the collapse occurred, was often relegated to philosophical discussions rather than considered a core physics problem. However, a small but persistent group of physicists continued to grapple with these fundamental questions, seeking alternatives to the Copenhagen dogma. They found its reliance on an ill-defined observer, and the arbitrary nature of wave function collapse unsatisfactory. They sought a more complete, objective description of reality, one that did not require an external act of observation to solidify existence. One such individual was Hugh Everett III, a brilliant and iconoclastic young physicist. Born in 1930, Everett pursued his doctoral studies at Princeton University in the mid-1950s, a period when the foundational issues of quantum mechanics were still hotly debated, albeit often behind closed doors. His advisor was John Archibald Wheeler, a towering figure in theoretical physics, known for his work on general relativity and quantum gravity. Wheeler, though a proponent of the Copenhagen interpretation, recognized Everett's intellectual prowess and encouraged his unconventional thinking. Everett was deeply troubled by the measurement problem and the arbitrary distinction between the quantum system and the observer. He questioned why the laws of quantum mechanics, which applied so successfully to microscopic particles, should suddenly break down when applied to macroscopic measurement devices, or, indeed, to human observers. He believed that quantum mechanics, SH, would be a universally applicable theory, without special pleading for observers or measurement events. His groundbreaking work began in 1954, culminating in his 1957 PhD thesis, initially titled The Theory of the Universal Wave Function. In this thesis, Everett proposed a radical and audacious solution to the measurement problem, one that would forever alter the landscape of quantum foundations: the many worlds interpretation, MWI. Everett's central insight was to take the Schrödinger equation, the fundamental equation describing how quantum systems evolve over time, literally. The Schrödinger equation, unlike the Copenhagen interpretation, does not describe wave function collapse. Instead, it describes a continuous, deterministic evolution of the wave function. Everett argued that the wave function never truly collapses. Instead, when a measurement is made, or when a quantum system interacts with another system, like a measuring device or an observer, the universe itself splits, or branches, into multiple parallel universes. Each branch corresponds to one of the possible outcomes of the quantum measurement. In one branch, the electron spins clockwise. In another, it spins counterclockwise. In one branch, Schrödinger's cat is alive. In another, it is dead. All these outcomes, according to Everett, are equally real. This was a profound departure from the prevailing view. Instead of a single reality where probabilities determined which outcome manifested, Everett proposed a multiverse where every possible quantum outcome was realized in its own distinct universe. The observer, rather than causing a collapse, simply becomes entangled with the observed system, and their own state splits along with it. When you observe a coin toss, in Everett's view, you don't merely see one outcome. Instead, you split into two versions of yourself, one observing heads in one universe and another observing tails in a parallel universe. Both versions are equally real, equally conscious. Everett's initial thesis was a dense, highly mathematical treatise. It presented a relative state formulation of quantum mechanics, where the state of an observer is always relative to the state of the observed system, and vice versa. There is no absolute state of the universe, only relative states. This meant that the universe, as a whole, is always in a superposition, but individual observers within it only experience one branch of that superposition. The perceived collapse of the wave function from an observer's perspective is simply the observer becoming correlated with a specific outcome in their particular branch of the universe. The implications of Everett's proposal were staggering. It offered a way to resolve the measurement problem without introducing any arbitrary collapse postulate or ill-defined observer. The quantum world was inherently deterministic and unitary, evolving according to the Schrödinger equation, and the probabilistic nature we experience arises from our own splitting and subsequent awareness of only one specific branch. It eliminated the need for an external classical realm or a special role for consciousness in quantum mechanics. The entire universe, including observers, was treated as a quantum system. Everett's doctoral thesis, ultimately titled Relative State Formulation of Quantum Mechanics, was completed and submitted in 1957. It was a radical and deeply challenging work, one that dared to question the very foundations of accepted quantum dogma. The initial reception to Everett's radical ideas was, understandably, muted and often dismissive. The physics community, deeply entrenched in the Copenhagen interpretation, found the notion of an infinite multitude of parallel universes to be scientifically outlandish and philosophically extravagant. It flew in the face of conventional wisdom and seemed to introduce an unnecessary layer of complexity, rather than simplifying the quantum enigma. John Wheeler, Everett's advisor, despite his initial encouragement, harbored significant reservations. He recognized the mathematical elegance of Everett's work, but struggled with its ontological implications. In April 1957, Wheeler arranged for Everett to visit Niels Bohr in Copenhagen, hoping to bridge the conceptual chasm between the two interpretations. It was a fateful meeting, one that would deeply impact Everett and the immediate trajectory of his theory. The encounter between the young, audacious Everett and the formidable, revered Bohr was famously difficult. Bohr, accompanied by his protege Oj Peterson, remained steadfast in his commitment to the Copenhagen interpretation. He saw Everett's approach as a return to a pre-quantum, classical realism, denying the fundamental role of observation in shaping reality. The discussions, which stretched over several days, were characterized by a profound misunderstanding and an inability to find common ground. Bohr and his colleagues simply could not accept the idea of an ever-branching universe, finding it metaphysically unacceptable. Everett left Copenhagen disheartened, his revolutionary ideas largely unappreciated by the very giants of quantum theory he had hoped to impress. Upon his return to Princeton, Everett found himself in a difficult position. Wheeler, while still supportive of Everett personally, was swayed by Bohr's steadfast opposition and the broader community's skepticism. He pressed Everett to modify his thesis, softening its more radical ontological claims about branching universes. Everett, under pressure, reluctantly agreed to revise his original, more expansive manuscript, producing a shorter, more cautious version for publication. This abridged version, titled Relative State Formulation of Quantum Mechanics, appeared in the Reviews of Modern Physics in July 1957, a less provocative title than his initial Theory of the Universal Wave Function. It emphasized the mathematical formalism and the relative state concept, downplaying the explicit branching into multiple worlds, though the implications were still inherent in the mathematics. Even with the toned-down publication, the scientific community largely ignored Everett's work. It was too far removed from the prevailing paradigm, too audacious in its claims. Everett himself, disillusioned by the lack of recognition and the difficulty of pursuing such unconventional research within academia, soon left theoretical physics. In 1956, even before his thesis was published, he had already taken a position with the Weapons Systems Evaluation Group, WSEG, at the Pentagon, applying mathematics to military problems. He later went on to a successful career in operations research and computer science, pioneering early forms of parallel computing and the generalized Lagrange multiplier technique. The world of quantum foundations lost one of its most original thinkers, at least for a time. For nearly a decade after 1957, Everett's many worlds interpretation languished in obscurity, a curious footnote in the history of quantum mechanics. It was occasionally mentioned, often dismissively, in specialized circles, but it never gained significant traction or widespread discussion. The Copenhagen interpretation, with its pragmatic, shut up and calculate ethos, continued to dominate quantum thought. However, the seeds Everett had planted would eventually find fertile ground. A small number of physicists, dissatisfied with the conceptual ambiguities of Copenhagen, continued to explore alternatives. Among them was Bryce DeWitt, a prominent theoretical physicist known for his work on quantum gravity and general relativity. DeWitt, based at the University of North Carolina at Chapel Hill, independently arrived at conclusions similar to Everett's in the mid-1960s, troubled by the measurement problem in the context of a quantum theory of gravity. He found the idea of a universal wave function, encompassing the entire cosmos, deeply appealing, as it offered a consistent framework for quantum mechanics without an external observer. DeWitt first encountered Everett's 1957 paper in 1965 and immediately recognized its profound significance. He became a fervent champion of the many worlds interpretation, understanding that Everett had already articulated the very solution he had been seeking. DeWitt was instrumental in resurrecting Everett's ideas from obscurity. He actively corresponded with Everett, encouraging him to revisit his original, more comprehensive thesis manuscript, which contained the explicit concept of branching universes. In 1970, DeWitt, along with Neil Graham, edited and published a landmark collection of papers titled Asterisk, The Many Worlds Interpretation of Quantum Mechanics. This volume, published by Princeton University Press, included Everett's original, unabridged 1957 PhD thesis, along with his shorter 1957 Reviews of Modern Physics Asterisk paper, and several new contributions from DeWitt and others. The publication of this book was a pivotal moment for the MWI. For the first time, Everett's full, unexpurgated vision of a branching multiverse was made widely available to the physics community. DeWitt's own contributions to the volume were crucial. He not only brought Everett's work to a broader audience, but also provided a clear, accessible exposition of the MWI, explaining its implications in a way that resonated with many. He coined the term many worlds interpretation itself, which quickly became the standard moniker for Everett's theory. DeWitt's writings vividly described the branching process, picturing the universe constantly splitting into an ever-growing number of parallel realities with every quantum event. He grappled with the implications of this branching for our sense of identity and the nature of consciousness, acknowledging the mind-boggling aspects of the theory. The 1970 book sparked a renewed interest and debate surrounding the MWI. Suddenly, a theory that had been largely ignored for over a decade was thrust into the spotlight of quantum foundations. While still controversial, it could no longer be easily dismissed. DeWitt's advocacy gave the MWI a legitimacy it had previously lacked, and his stature in the physics community ensured that the ideas would be taken seriously. Beyond the formal publication of Everett's work, the 1970s and early 1980s saw the MWI gain traction through various informal channels and broader discussions. Conferences on quantum foundations, though still relatively niche, began to include sessions dedicated to Everett's ideas. Physicists who had long been uncomfortable with the Copenhagen interpretation's measurement problem found in MWI a compelling, if radical, alternative. One of the persistent criticisms of the MWI, particularly in its early formulations, concerned the origin of probabilities. If all possible outcomes of a quantum measurement are realized in different branches, how do we explain the probabilistic nature of quantum mechanics that we observe? Why do we experience a 50% chance for a particle to spin up and a 50% chance for it to spin down, rather than simply witnessing both? This was known as the measure problem, or the Born rule problem, within the MWI. This challenge was addressed in part by the burgeoning field of decoherence theory, which began to emerge as a significant area of research in the late 1970s and 1980s. Decoherence offered a mechanism by which quantum superposition, typically observed only in isolated microscopic systems, appears to vanish in the macroscopic world. It explained how the interaction of a quantum system with its environment, even a seemingly innocuous one, causes the system's quantum coherence to rapidly dissipate, leading to a classical-like behavior. Pioneering work by physicists like H. Dieter Zeh in the 1970s laid the groundwork for decoherence. Zeh, in particular, emphasized the role of the environment in destroying quantum coherence and creating classical appearances. He argued that the collapse of the wave function, as described by Copenhagen, was not a fundamental process, but rather an emergent phenomenon resulting from the entanglement of a quantum system with its vast, complex environment. Wojciech, then at the California Institute of Technology and later at Los Alamos National Laboratory, further developed decoherence theory in the 1980s. Zherk showed how the interaction of a quantum system with its environment effectively selects a preferred basis of states known as pointer states, which are robust against environmental perturbation. These pointer states correspond to the classical outcomes we observe. For instance, a quantum particle's position, when interacting with a measuring device or the surrounding air molecules, quickly decoheres into a definite position, even though the underlying universal wave function remains in a superposition. The advent of decoherence theory provided crucial support for the many worlds interpretation. It offered a rigorous physical mechanism for why we only perceive one classical outcome from an inherently quantum superposition. In the MWI framework, decoherence explains why the branches of the universe become effectively distinct and non-interacting. Once a system decoheres, its different branches no longer interfere with each other, making them appear as separate, parallel realities to observers within those branches. Decoherence thus provided a natural explanation for the apparent collapse, without invoking any non-unitary or ad hoc process. It showed how the classical world emerges from the quantum world, not through a mysterious collapse, but through the universal application of quantum mechanics itself. Decoherence also offered a potential solution to the Born rule problem. While not fully resolved, later work building on decoherence particularly by David Deutsch and others, began to explore how the probabilities we observe in quantum mechanics could emerge naturally from the structure of the branching universe, even if all outcomes are realized. The argument centered on the idea that observers within a given branch, through their subjective experience and decision-making, would effectively perceive probabilities consistent with the Born rule. The combined force of DeWitt's tireless advocacy and the theoretical elegance of decoherence theory significantly boosted the credibility and visibility of the many worlds interpretation. It moved from being an obscure, radical idea to a serious contender in the ongoing debate about the foundations of quantum mechanics. While still facing significant conceptual and philosophical challenges, MWI had found a powerful ally in decoherence, which provided a much-needed physical mechanism for its branching postulate. The 1970s and 80s solidified MWI's position as a legitimate, albeit controversial, interpretation, paving the way for further exploration and debate in the decades to come. The 1980s and 1990s witnessed a growing number of physicists and philosophers grappling with the implications of the many worlds interpretation. Figures like David Deutsch, a theoretical physicist at the University of Oxford, became prominent advocates, further developing the MWI and arguing for its profound consequences for computation and the nature of reality. Deutsch, in his seminal 1985 paper, Quantum Theory, the Church-Turing Principle, and the Universal Quantum Computer, used the MWI to explain the power of quantum computation, suggesting that quantum computers perform calculations in parallel across multiple universes. His work provided a concrete, practical application for the MWI, demonstrating how it could offer a deeper understanding of computational processes that classical physics could not. Beyond the realm of quantum foundations, the concept of parallel universes began to seep into popular culture, albeit often in a highly sensationalized and simplified form. Science fiction novels, films, and television shows increasingly explored themes of alternate realities, parallel Earths, and branching timelines. While these portrayals rarely captured the nuanced scientific arguments, they ingrained the idea of a multiverse in the public consciousness, making it a familiar, if fantastical, concept. This popularization, however, also led to a significant amount of misunderstanding and conflation of different multiverse theories. As the 20th century drew to a close, the scientific landscape was undergoing a profound transformation. Quantum mechanics, despite its immense success, continued to present deep conceptual puzzles, particularly the measurement problem. At the same time, cosmology was grappling with its own set of mysteries, from the origin of the universe to the nature of dark matter and dark energy. It was in this fertile intellectual environment that the idea of a multiverse, once confined primarily to the MWI, began to emerge from entirely different branches of physics. One of the most significant developments came from the realm of string theory, which began to gain considerable traction in the 1980s and 1990s. String theory posits that the fundamental constituents of the universe are not point-like particles, but rather tiny, one-dimensional vibrating strings. A key feature of string theory is its requirement for extra spatial dimensions beyond the familiar three. While initially viewed as a mathematical curiosity, these extra dimensions became central to the theory's ability to unify all fundamental forces, including gravity, in a consistent quantum framework. However, the existence of these extra dimensions posed a problem. Why do we not observe them? The answer, as developed within string theory, was that these dimensions are compactified, curled up into tiny, unobservable spaces. But the way in which these dimensions could be compactified was not unique. In fact, string theory predicted an astronomical number of ways, often estimated at 10^500, in which the extra dimensions could be curled up. Each distinct compactification would give rise to a different set of physical laws, different fundamental constants, and potentially different types of particles. This vast landscape of possible compactifications, often referred to as the string landscape, inherently implied a multiverse. Each distinct compactification could be thought of as a different pocket universe or brain world, each with its own unique physics. This was not a multiverse arising from quantum measurements, like the MWI, but rather a multiverse arising from the fundamental mathematical structure of a proposed theory of everything. The sheer number of possibilities in the string landscape suggested that our universe, with its specific physical laws and constants, might just be one of an incomprehensibly large ensemble of universes. The concept of the string landscape was further elucidated by researchers like Leonard Susskind, who became a prominent advocate for the idea in the early 2000s. Susskind and others argued that the string landscape provided a natural explanation for the fine-tuning of the universe's fundamental constants, particularly the cosmological constant, which governs the accelerated expansion of the universe. The observed value of the cosmological constant is incredibly small, a fact that poses a significant challenge for theoretical physics. In the string landscape, however, this fine-tuning could be explained by anthropic reasoning. We observe a universe with these specific values because only such a universe could support the emergence of life and observers like us. In this view, countless other universes in the landscape would have different, life-unfriendly values. Simultaneously, another theoretical framework, loop quantum gravity, LQG, also began to hint at multiverse-like structures. Loop quantum gravity is a theory that attempts to quantize spacetime itself, rather than treating it as a fixed background. It proposes that spacetime is not continuous, but rather composed of discrete loops or quanta of gravitational fields. While LQG does not explicitly predict a multitude of parallel universes in the same way as MWI or the string landscape, some of its implications suggest a cyclical or rebounding universe, which can be interpreted as a form of cosmological multiverse. One key aspect of loop quantum gravity is its potential to resolve the singularity problem at the heart of the Big Bang. In classical general relativity, the Big Bang is a singularity where spacetime curvature becomes infinite, and the laws of physics break down. However, in LQG, the quantum nature of spacetime prevents this singularity. Instead, it suggests a big bounce, where the universe contracts to a minimum size known as a quantum bounce, and then expands again. This implies that our current expanding universe might have emerged from the collapse of a previous universe. This big bounce scenario, championed by physicists like Martin Bojold and Abhay Ashtekar, opens the door to a cyclical multiverse, where universes are born, expand, contract, and bounce back into existence in an endless cycle. Each cycle could potentially have different initial conditions and evolve into a universe with different properties. While not parallel, in the sense of existing simultaneously in the same spacetime, these serial universes constitute a form of multiverse, where our universe is but one iteration in an eternal cosmic dance. The details of how information or properties might carry over from one bounce to the next remain a subject of active research and debate within the LQG community. Perhaps the most pervasive and influential source of multiverse concepts in the late 20th and early 21st centuries came from inflationary cosmology. Inflationary theory, first proposed by Alan Guth in 1980, was developed to solve several puzzles of the standard Big Bang model, such as the horizon problem and the flatness problem. It posits that the very early universe underwent a period of extremely rapid, exponential expansion, far exceeding the speed of light, lasting for a tiny fraction of a second. This inflationary epoch smoothed out the universe, made it spatially flat, and generated the initial density fluctuations that later grew into galaxies and clusters. While Guth's original model provided a powerful solution to cosmological problems, it was later refined and extended by Andre Linde and others, leading to the concept of eternal inflation. In eternal inflation, the inflationary process, once started, never truly stops everywhere. Instead, it continues indefinitely in most regions of spacetime, constantly spawning new bubble universes or pocket universes. Our observable universe in this view is just one such bubble, a region where inflation has ended and the hot Big Bang has commenced. Linde's chaotic inflation model, developed in the mid-1980s, provided a robust mechanism for eternal inflation. He argued that the scalar field driving inflation, known as the inflaton field, could fluctuate quantum mechanically. In some regions, these fluctuations might be large enough to sustain inflation, leading to new inflationary regions, while in others, inflation might end, forming a new pocket universe. This process repeats indefinitely, creating an infinitely vast and diverse multiverse. Each bubble universe within this eternally inflating multiverse would be causally disconnected from the others, meaning that events in one bubble cannot affect events in another. They would effectively be separate universes, each potentially with its own unique physical laws and fundamental constants, much like the string landscape. The parameters of the inflaton field, the energy scale of inflation, and the way inflation ends could vary from one bubble to the next. The concept of eternal inflation provides a natural context for the anthropic principle, similar to the string landscape. If there is an infinite number of universes, each with different physical parameters, then it is not surprising that we find ourselves in one that is hospitable to life. The fine-tuning of cosmological constants, such as the cosmological constant itself or the strength of fundamental forces, can be explained as a selection effect. We exist in a universe where these values allow for our existence. Other universes with different values simply would not contain observers. The convergence of these distinct theoretical frameworks, the many worlds interpretation from quantum mechanics, the string landscape from string theory, the big bounce from loop quantum gravity, and eternal inflation from cosmology, dramatically reshaped the scientific understanding of the multiverse. It was no longer a singular, niche idea, but a multifaceted concept arising from different, often independent, lines of inquiry in fundamental physics. By the late 20th and early 21st centuries, the multiverse had transitioned from a philosophical curiosity to a serious, albeit still highly speculative, component of leading theories attempting to describe the universe at its most fundamental level. This confluence of ideas, emerging from disparate corners of physics, solidified the multiverse as a major conceptual force by the early 21st century. However, this rise in theoretical prominence also ignited a fierce debate, particularly concerning the scientific status of these new cosmological paradigms. The central challenge quickly became one of testability and falsifiability. How could one empirically verify the existence of universes beyond our own, and what would constitute evidence against such theories? Philosophers of science, alongside many physicists, began to raise fundamental questions. Karl Popper's criterion of falsifiability, a cornerstone of scientific methodology, states that a theory must be capable of being proven false by observation or experiment to be considered truly scientific. Multiverse theories, by their very nature, often posited universes that were causally disconnected and inherently unobservable from our own. This led to accusations that they were moving into the realm of metaphysics rather than empirical science. Prominent critics emerged, arguing that the multiverse represented a dangerous trend in theoretical physics. Paul Steinhardt, a cosmologist at Princeton University and one of the architects of inflationary theory, expressed growing concerns about the untestability of eternal inflation models, particularly in their more extreme interpretations. He, along with others, suggested that the flexibility of such models, capable of explaining almost any observed outcome through a suitable choice of bubble universe, rendered them effectively unfalsifiable. If any universe could exist with any set of laws, then the existence of our specific universe, no matter how improbable, could always be explained away as simply one outcome among an infinite ensemble. George Ellis, a renowned cosmologist and co-author with Stephen Hawking on the large-scale structure of spacetime, became another vocal critic. Ellis argued forcefully that if a theory cannot be tested, even in principle, it falls outside the purview of science. He contended that, while multiverse concepts might be mathematically elegant, their lack of empirical grounding made them more akin to philosophical speculation or even religious belief than scientific hypothesis. He emphasized the importance of distinguishing between what is mathematically possible and what is physically real, stressing that without observational evidence, the multiverse remained firmly in the former category. The anthropic principle, often invoked to explain the fine-tuning of our universe within a multiverse context, also faced significant scrutiny. While proponents saw it as a powerful explanatory tool, critics like Roger Penrose argued that it was often used as a principle of last resort, a way to explain away otherwise intractable problems without offering true predictive power. Penrose suggested that the anthropic principle, when applied to a vast multiverse, could explain anything and therefore nothing, eroding the predictive strength of physics. He and others sought more fundamental, non-anthropic explanations for the universe's observed properties. Despite these criticisms, many advocates of multiverse theories maintained their scientific validity, often redefining what constituted testability in the context of cosmology. Leonard Susskind, for instance, in his defense of the string landscape, argued that while we cannot directly observe other universes, the very existence of the landscape provided a framework for understanding why our universe possesses its particular properties. He suggested that the predictive power of the string landscape lay not in predicting the existence of specific other universes, but in explaining the observed values of fundamental constants within our own. If future, more precise measurements of cosmological parameters were to strongly contradict the predictions derived from the anthropic selection within the landscape, then the theory could, in principle, be falsified. Similarly, some proponents of eternal inflation, such as Andre Linde, pointed to potential signatures of other universes that might, in principle, be detectable. These could include subtle imprints in the cosmic microwave background radiation, the afterglow of the Big Bang, caused by collisions with other bubble universes. While such observations remain far beyond current technological capabilities, the mere possibility of their existence, however remote, was offered as a counterargument to claims of absolute untestability. Researchers like Matthew Johnson at York University and Anthony Aguirre at UC Santa Cruz have explored theoretical models for detecting such bruises on our cosmic horizon, though concrete evidence remains elusive. The many worlds interpretation, in particular, presented a unique challenge to the testability debate. Since all branches of the quantum wave function are equally real, and observers within each branch experience a unique outcome, how could one ever prove that other branches exist? David Deutsch, however, continued to argue that the MWI was empirically testable, albeit indirectly. He pointed to the phenomena of quantum interference and entanglement as evidence of the parallel computation occurring in other branches. For Deutsch, the very success of quantum mechanics and the practical realization of quantum computing were, in a sense, indirect evidence for the existence of parallel worlds. He maintained that the MWI offered the most parsimonious explanation for these quantum phenomena, despite the conceptual leap it required. The debate extended beyond the scientific community, penetrating deeply into philosophical discourse. Philosophers of physics, such as Max Tegmark, a cosmologist at MIT, actively engaged in classifying and analyzing different types of multiverses. Tegmark's mathematical universe hypothesis proposed that our physical reality is a mathematical structure, and that all mathematically consistent structures exist. This radical view implied a level IV multiverse, encompassing all possible mathematical realities, making it the most expansive and, arguably, the most challenging to reconcile with traditional notions of empirical science. Tegmark's work, particularly his 2014 book, Our Mathematical Universe, brought these deep philosophical questions to a wider audience, prompting discussions on the nature of reality, existence, and the limits of human understanding. Philosophers like Nick Bostrom at the University of Oxford explored the ethical and existential implications of multiverse theories. His work on observation selection effects and the simulation hypothesis directly grappled with the consequences of living in an unimaginably vast or even simulated multiverse. Bostrom's arguments, such as the doomsday argument, which suggests that the total number of humans who will ever live is likely not astronomically large, implicitly rely on statistical reasoning within a multiverse framework. These philosophical inquiries, while not directly providing empirical evidence, highlighted the profound impact that multiverse concepts could have on our understanding of ourselves and our place in the cosmos. The philosophical implications also touched upon the very definition of scientific explanation. If the multiverse explains everything, does it truly explain anything? This question resonated with concerns about the God of the Gaps argument, where divine intervention is invoked to explain phenomena not yet understood by science. Critics feared that the multiverse could become a multiverse of the gaps, an all-encompassing explanation that stifled further inquiry into fundamental physical laws. As these intense scientific and philosophical debates unfolded, the concept of parallel universes continued its inexorable march into popular culture. The late 20th and early 21st centuries witnessed an explosion of media that embraced and often creatively reinterpreted multiverse ideas. Films like Sliding Doors, 1998, explored the concept of divergent timelines stemming from a single decision, while television series such as Fringe, 2008-2013, and Rick and Morty, 2013-present, brought sophisticated, often comedic, portrayals of parallel Earths and interdimensional travel to millions of viewers. The Marvel Cinematic Universe, beginning in 2008 with Iron Man and dramatically expanding its scope, fully embraced the multiverse in its later phases, notably in films like Spider-Man, No Way Home, 2021, and Doctor Strange in the Multiverse of Madness, 2022. These blockbusters introduced audiences worldwide to the idea of infinite variations of familiar characters and realities, making the multiverse a household term. Even independent films, such as the critically acclaimed Everything Everywhere All at Once, 2022, used the multiverse as a backdrop for deeply personal narratives, showcasing its versatility as a storytelling device. Video games also extensively utilized multiverse tropes, offering players choices that led to branching narratives and alternate endings, directly mirroring the MWI. Games like BioShock Infinite, 2013, and Life is Strange, 2015, explored the profound emotional and philosophical consequences of parallel realities and choices. This cultural penetration, while undeniably exciting, also contributed to a blurring of lines between scientific theory and speculative fiction. The public imagination, often captivated by the more fantastical elements of parallel worlds, sometimes struggled to differentiate between the nuanced, mathematically driven arguments of physicists and the more dramatic, narrative-driven portrayals in entertainment. The scientific rigor, the subtle distinctions between different types of multiverses, quantum, cosmological, string theoretic, often got lost in translation. By the second decade of the 21st century, the myth of parallel universes had become a complex tapestry woven from cutting-edge theoretical physics, profound philosophical inquiry, and pervasive popular culture. It stood as a testament to humanity's enduring fascination with the unknown, with what lies beyond our immediate perception. The debate over its scientific validity, its testability, and its implications continues, robust and unresolved. Whether these parallel worlds are a profound truth of reality, a necessary consequence of our most successful scientific theories, or merely an elegant mathematical construct with no empirical counterpart, remains the most tantalizing question. The journey to understand our universe, and perhaps others, is far from over, reminding us that the boundaries of knowledge are constantly shifting, and the greatest mysteries often lie just beyond the edge of what we can currently see or comprehend.